Hello class, in this video I'm going to go over how to control a stepper motor with a microcontroller. In addition to what's taught in class, this video is going to be a great resource for getting your final project off the ground because obviously precise control of a motor is very important. This stepper motor cannot be directly connected to the Arduino for two main reasons. The first is that it draws way too much current. Some stepper motors will draw amps, maybe even tens of amps worth of current, and these pins are only good for a fraction of that load. The other reason is that in order to be able to get this motor to work correctly, we need to be able to drive current in both directions through the two different sets of coils, which is just not possible with these pins. So what we need is a stepper driver. This takes digital signals from the Arduino, and depending on the position of the rotor of the stepper motor, it coordinates the flow of current through these wires. There's actually quite a bit of logic in this integrated circuit, but it's going to be a black box for us. What's important is that we feed it the correct input signals and get out the expected output, which in our case is going to be precise control of this rotor. If we flip this board over, we can see the labels for all the pins. Starting in the top left, we've got the direction signal. This is going to determine if the shaft rotates clockwise or counterclockwise. Then we've got the step signal. Every time input's received on this pin, the motor shaft will rotate incrementally, hence its name, the stepper motor. We've got sleep and reset. We'll ignore those for now. Down here, these pins, they actually say MS3, MS2, and MS1. Those are micro-stepping levels. Interfacing with those pins will increase or decrease the size of the step, which ultimately affects the resolution of the movement. This enable pin down here will determine if the stepper motor is active or not. Next, we've got ground and VDD. This supplies the power for the logic of the board. We're going to come back to this because these pins are very important that we get correct. Next, we have the 4 pins for the 2 coils of the stepper motor. Then we have another ground and then the positive supply of power for the stepper motor. Stepper motors perform better at higher voltages. The Arduino, recall, operates at 5 volts, which is much too low for controlling a stepper motor. The limiting factor for voltage in our case is going to be the stepper driver. This is only rated for, I think, 36 volts. We're going to be using 24 volts, but introducing 24 volts to our circuit poses a problem. The Arduino, even through its regulated power input, if it's fed 24 volts, it'll fry the microcontroller. As I had mentioned, the driver board requires its own power source, 5 volts, in order to be able to perform the logic to coordinate the movement of the stepper motor. If we mix up the power for the motor with that going to the driver board, that'll fry the driver board. I recommend taking a picture of the back of the stepper driver so that you can remember what these pins are. I like to use this potentiometer or Phillips head screw as a reference point for orienting myself with the pins on the board. We flip it over, they're going to be upside down, but we can see when this is seated in the breadboard like this, on the bottom right side we're going to have ground and then the power supply for the driver. Again, 5 volts there. These pins are all different. We don't want them to be connected to each other, so we're going to seat the board where the pins fall on either side of this divide. Next, let's talk about supplying the power for the logic of the microcontroller and the driver, as well as the power for the stepper motor. We're going to use this quad power supply. It gets its name because it outputs 4 different voltages, which we can read from the side of the supply. We've got positive 5 volts, positive 12 volts, positive 24 volts, negative 12 volts. These correspond to V1, V2, V3, and V4 respectively. Before I go any further, when working on a circuit with a regulated power supply like this one, always unplug it and never eat or drink near it. And when you're done prototyping for the day, make sure you unplug this guy. Also, we have exposed terminals here. When this is plugged in, it could shock you. So do not stick your finger or screwdrivers or anything in here when it is on. If you see exposed wires here, just let me know and I can fix them. Again, we need 5 volts for the Arduino and for the stepper driver, as well as 24 volts for the motor. Unfortunately, the only way we can feed the Arduino 5 volts is through this USB connector. Through the barrel jack, we can give it 7 or 12 volts. And we're in luck because on the side of our power supply, we have, again, V2 is equal to 12 volts. All 4 of these voltages share the same common ground or negative pin, however you want to refer to it. In this case, on the power supply, it's labeled common. It would be ideal if we could supply 5 volts to the Arduino. This power supply outputs it, but unfortunately we can only feed 5 volts into it through the USB connector. And it's not realistic to add such a connector onto the wires coming out of this power supply. So instead, we're going to supply it 12 volts because the barrel jack can take 7 to 12 volts. We can either use a barrel jack connector, which I may supply in the future, but for this case, I'm going to go in through the VN pin on the side of the board. The VN pin is connected to the barrel jack, so this is equivalent to plugging in a barrel connector. Once the 12 volts goes in through the VN pin, it'll be stepped down to a manageable 5 volts through these components over here. V2 is 12 volts. I've wired these power supplies to have 2 connections to 12 volts so that 2 people can independently be working on this circuit. If it's just you working on it, then make sure you plug both wires in just to prevent any shorts from occurring. So we'll plug in the yellow. Yellow is positive 12 volts, black is ground or negative. I'm going to plug the other one in as well. I'm going to bring this 12 volts in to the Arduino through the VN pin. I'm also going to connect the ground to complete the circuit from the power supply to the ground pin on the Arduino. So on my left power rail right here, where all the pins are connected in each column, is 12 volts. We need to keep that in the back of our head. On the right side, I'm going to have 24 volt power. On this power supply, that's V3, which is connected to the red wires. Again, it's only me working on this power supply, so I'm going to plug in both of these connectors. If we connect the Arduino in any way to this 24 volt power, we're going to get some magic smoke coming out of the microcontroller. That would not be good. So we need to be really careful with this power rail. It basically only needs to connect to that VMOT pin. To get the 5 volts to allow the driver to operate, we can pull that off the Arduino. We'll go to the 5 volt pin and connect it to VDD. For the ground connection, we can use either negative power rail because all of the grounds or commons are connected together, or we can use the ground on the Arduino. I'm just going to use the one closest. Next, we can focus on the power supply for the motor. VMOT is this top right pin over here. Connected to the positive 24 volts. We can connect the ground, which is the second pin from the top right, to the negative rail as well. Next, we're going to connect the step and direction pins to the Arduino, and this is how the Arduino coordinates the movement of the stepper motor through the driver. The rate and the amount of step pulses sent to the driver will determine how quickly and how far the motor moves respectively. And of course, the direction pin is going to be whether the motor rotates clockwise or counterclockwise. If the potentiometer is on the bottom closest to you, the direction pin is the bottom left pin. I'm going to connect it to digital pin 2 on the Arduino. The next pin up is the step signal. I'm going to connect that to digital pin 3 on the Arduino. Green is direction, orange is step. The last necessary step before connecting the motor is to tie the sleep and reset buttons together. Without this connection, the reset pin is floating and this will just keep resetting and you're not going to get any movement. Don't forget this guy. This is probably the most commonly forgotten connection. Now we can connect the motor. The direction you plug the motor in will determine which way it rotates given a direction signal. So one way, when the direction signal is high, will rotate it clockwise, and the other way of plugging in the motor into the board will cause it to rotate counterclockwise when that signal is high. This is more so just preference. I'm going to double check my connections. Everything looks good. I can now plug the power supply in. The code was already uploaded to the Arduino. Everything's working. Kind of get a feel for how quickly this is moving. I can double the number of steps required for this motor to complete one full rotation, which will increase its resolution by connecting microstep 1 pin to 5 volts. 5 volts is on this row right here. Again, I unplugged the power supply before I started doing any wiring. Let's go ahead and plug it in again and see if the speed of the motor changed. It's about half the speed. If we connect all the microstep pins to 5 volts, we will turn one full step into 16 microsteps. This motor is moving 1/16 the speed of the original configuration. Not only do you get smaller possible movements, but you also get smoother motion as well. The last pin that I want to talk about is this one in the top left. This is the enable pin. The driver board is enabled by default. If you pull this pin high, it'll disable the driver, consequently disable the motion of the motor. This could be a useful safety feature. Next, let's hop into the code that's making this motor rotate. Okay, we're now in the Arduino programming environment, and we're looking at the code that I used to drive the motor as I was testing the wiring. In order to drive the motor, we're going to call a library called AccelStepper. If you don't have this installed, you'll have to go to Tools, Manage Libraries, search AccelStepper, and here it is. Version 1.61 is what I'm on. Once we include this library in our Arduino sketch, we unlock a lot of functionality without having to do much coding, which is always a win. To learn all about what you can do with this library, I recommend that you go to the AccelStepper webpage. I'll post a link for this below this video, as well as on Brightspace. Here are all the different functions that we can call in order to achieve different effects. I'm going to leave this open-ended as I would like for you to explore these functions as you work on your final project, but I'm going to cover the most important ones here. At the top of the code, again, we're telling the Arduino IDE to include the AccelStepper library. Under this, we've got what is known as a constructor, and this is basically setting up a stepper motor, in this case called StepperX. This bit right here says that the stepper motor is being driven by a stepper motor driver, and the next number right here is the pin for the step signal, followed by the pin number for the direction signal. It's important that if we want to make StepperX move, we need to refer to it as StepperX. The constructor is above void setup. Void setup, which is run once at startup, includes a couple settings for our motor. Here we are setting the maximum speed of StepperX, which is 1,000 watt. In this case, it's 1,000 steps per second. A common conversion when programming stepper motors is the number of steps per rotation. Without any microstepping enabled, most stepper motors have 200 steps per rotation. So in this case, our maximum speed is 5 rotations per second, 1000 divided by 200. This max speed by default is 1 step per second, which is incredibly slow. So we have to increase this maximum speed before our next line, which is the speed at which we want to run the motor at. Stepper x dot set speed is 50. 50 divided by 200 gives us a quarter rotation per second, or it'll take us 4 seconds to make 1 rotation. Finally, in our void loop, which runs continuously after the void setup, we just tell our stepper motor to run at our set speed. This function is called run speed. Stepper x dot run speed, it'll now rotate at 50 steps per second. This will occur forever. It's great to play around with the speed of the motor, but make sure that what you expect to happen is actually occurring in real life. And remember, the speed of your motor based on the code is a result of the number of steps per rotation. So if you increase the number of steps per rotation through microstepping, then you're going to have a slower overall speed if you run the same code. Definitely try enabling different amounts of microstepping and running the exact same code to see the effect of this. Let's say we want to use our motor to move a linear actuator known distances. I'm going to pop over to this second window over here. The first 2 lines are the same. We're including the Excel stepper library and setting up that single stepper motor, which we're referring to as stepper X. The void setup is a little bit different. We've lowered our max speed to 200 steps per second. We've got a new setting here, acceleration. It's impossible to go from resting state to the desired speed instantaneously. There is some acceleration involved. The Excel stepper library allows us to directly control how quick or how slow that acceleration is. Finally, we have a function that tells our stepper X to move to 200 steps, which again, if the motor is being run at full steps, that's 1 rotation. And if that motor is driving a lead screw with an 8mm lead, then that 1 rotation is going to result in 8mm of linear motion of the nut. In the void loop, we've got this stepper x dot run. This is different than the stepper x dot run speed. This function checks as this loop runs continuously if the motor should be moved based on the max speed and the acceleration that we previously set. Once the motor takes 200 steps, nothing else will occur. We could add some logic here in order to have the motor run in reverse when a button's clicked. Really, the sky's the limit. I love working with motors because it's easy to see if the wiring and the code is working as expected, because that should all translate in some amount of rotation of the rotor. Let me know if you have any questions or concerns. Always unplug the power supply when working on the wiring, and make sure that you're very careful with those different voltages, as some can fry the Arduino and the stepper driver.